Okay, today what we'll do is we want to wrap up the discussion on absolute motion analysis, and we'll start today with a problem we left off with during the last class session, and then we want to move on to the relative velocity analysis. This is where we use vectors. And this is actually the most powerful approach to use for handling rigid body kinematics, is to use your vector approaches. So we'll be moving into this area with velocity. We'll spend a couple days on this, and then we'll deal with acceleration once you have a good grasp on this. Try to do, if you're behind on homework, which most of you are, try to do a scattering of the current problems, though, so that you'll kind of be present as far as then the discussion that goes on in class. So try to maybe at least tackle one or two of the current problems related to the class session before the next class session, so that when we're answering questions and things like that, it'll be a little more meaningful to you. Once you grasp the vector approach on relative velocity, then we can start looking at the acceleration stuff. And then that'll be getting close to the tail end of the content of the course. Okay? So let's go back to a problem that we were working on, we left off with from last class session. And that was number 29 in chapter 5. And I'll put it up on the screen here again. And I'll bring that on up some. Okay. And let me do the focus on that. That's reasonable, I guess. Okay, point A down here where my finger is, has a constant acceleration to the right, and that's sort of shown off here on the right side of the picture. Starts from rest with x equal essentially 0. So the crank arm and the connecting rod are essentially vertical at the start of the motion. Determine the angular velocity of link AB in terms of x and a. And they provide the answer, and it's only in terms of the x and a and length b for that omega. So what we observed, I'm going to go ahead and come up on the board now. What we observed with that problem was that the distance x can be described related to an angle off of the dotted line shown right there. So I'll redraw the figure. Length B, and this rod comes out here. And then this thing is, I think they labeled this A and this B. Is that correct? A here?
Yes.
Okay, thanks. And since both these arms, the crank arm and the connecting rod makes that triangle isosceles, consistently isosceles, then we have a description involving symmetric angles, equal angles right there. So what we did the other day is we wrote that this distance defined as x is equal to twice b cosine theta. Here's your b cosine theta. So we have x is equal to twice b cosine theta. We differentiated that, and we got x dot was equal to minus 2b sine theta theta dot, differentiating with respect to time. What we did not do last class session is notice that this is the omega right here. Here's the omega. So the omega is equal to x dot. Now x dot is the speed that this arm A is moving at, isn't it? Isn't this the velocity of point A, x dot? So this is the speed of point A. And so the speed, so this implies then that the omega is equal to the speed of point A divided by, and there's a negative on this, 2b sine theta. What we did last class session is we differentiated this thing a second time, and that's where we left off, right? We differentiated this a second time. And we ended up getting an x double dot was equal to minus 2b theta double dot sine theta minus 2b theta dot squared cosine theta. X double dot is the given value of this piston, accelerating to the right. Acceleration was equal to A's value, and that was given to us in the problem. So this x double dot was that, and this is where we left off with this thing. And we were at that point of pondering this when we ended class. Okay. So the problem with this description is that this involves the angular acceleration. We know we want the expression, and here's where our A is showing up, is it's down here in this thing. Now here's the omega we're looking for. We're looking for this expression for omega, but we've got this term involving the angular acceleration in here, which is rather troubling. So if we just leave a question mark on that and back up and see if we can come back up here and look at the expression on the velocity and see if we can move forward from this point. So let's see. The velocity of A is this speed right here, of x dot in other words. And they told us in the description of the problem that this arm began, the connecting rod and the crank arm here essentially started up here vertically and then moves out here with a constant acceleration. This constant acceleration. So what I think might be a smart idea is to come in here and look at this velocity, and we know that v dv equals a dx, where that is constant. That was given in the problem. So that means if we integrate that, with that being constant, from 0 to x, and this from they told us it was at rest initially, to some velocity v, we get 1/2 v squared equals ax, or v equals the square root of 2ax. So there's our velocity of point A right there. And no need for us, and it involves the acceleration A. So no need for us to have come down into this second derivative here. Feel good? Sometimes you got to backtrack a little bit. So we come back to this now, this expression for omega, and let's see, oh, we've got another little trouble spot, sine theta. Sine theta. Well, we know good old Pythagoras. So we know that sine theta is equal to the radical of 1 minus cos theta squared on the cosine. And look back up here in the kinematics, in the geometry here, that here's a definition of cosine theta in terms of x and b. So sometimes you have to look around a little bit, play with it. And so we have the expression for cosine theta here, which happens to be x over twice b. So we can plop that in there and drop that into this omega expression and our VA expression. And we get omega is equal to, I'm going to hang on to the negative for a second and then we'll talk about that when we get done. So we're dropping in the VA expression, which is the radical of 2ax. Down below we're dropping in 2b and our expression for the sine, which is the radical of 1 minus the square of the cosine. But the cosine is now x over 2b, and we have to square that. So we get this. And then what we'll do is tidy this up a little bit. Here we have a radical in the denominator. If we have a common denominator there, we could rewrite that as 4b squared minus x squared over the common 4b squared. But 2b outside the radical reduces out with a 4b squared inside. And we end up with the text answer excluding the negative. So what we would do is we would write down omega in their answers form, and I was looking at this a little while ago. And we come back now, and let's look at the picture here. Omega is the angular rate of change of this. Now this angle is collapsing, isn't it? This angle is collapsing, so indeed our negative was appropriate for the theta dot, or our omega. But what we could do is we could simply say that this arm, AB, has an angular velocity of this value, and it is rotating counterclockwise. So we would just assign a CCW onto that answer, which they did not do in their book, in the book. Okay? These different little things, like putting counterclockwise on the tail end of this is going to be useful for the rest of the course in regards to angular velocity and angular acceleration. Okay, doing that kind of a thing. And then also tidying up things such as this radical right here. And sometimes things like that back substitution on the cosine. Okay. All right. If we wanted to take a little extra time, we could imagine what this graph looked like, how omega would behave graphically for variable x. And of course we have a restricted domain here on x, don't we? Look back here at the physics. Yeah, it's locked in. It can't be any more than 2b. You can't at 0 to 2b. So this is restricted. X has a domain of 0 to 2b on the omega. Okay. And as x becomes close to 2b in value, this denominator, look at this denominator, as x approaches 2b, this denominator approaches 0. So that means that this angular velocity is driving up as x gets out there closer and closer to that extension of 2b. So graphically, if you wanted to image that, we would know that as we were coming out here, we're going to have asymptotic behavior out there, and this thing's going to be blowing up on us, something like that. And when x was 0, the angular velocity was what? 0, right? Numerator becomes 0. So what would the graph of that look like? I drew a portion of it here.
It looks like the tangent function, really.
Yeah, probably is going to maintain that concave upward character, I would expect. Now, without me thinking through it much more, let's just leave it at that. But we could take a few minutes and play with that. How would you play with that if you wanted to use your calculator? Put in some dummy values for A and B. You know, like maybe let the crank arm and the connecting rod length be 1, and pick some numeric value for A. And just drop them in there as numbers, and then go ahead and get that graphical characteristic, the general characteristic of that graph off your calculator then. And you could also scratch your head a little bit and think about this behavior without having to use the technology. Okay.
The values here, all these square roots, this looks like it's begging to be squared. Is there any physical significance to the omega squared value in this problem?
Omega squared, I don't think so. Not that I'm aware of. No, it's just that rigid body, that link. One thing not related to what you're talking about, though, here's something that'll be useful in our thinking a little later. What if we hooked a rigid body, say a sheet of cardboard, over the front of this, so you couldn't see this mechanism behind here, this crank arm mechanism? Let's say we hooked a sheet of cardboard and glued it on to that member AB. What we would be seeing in this motion is we'd be seeing this body carrying that omega. And it would be in translation, as you mentioned, as well. See it? Okay. So you can imagine hiding the actual mechanism behind these things and create some kind of a device. As a matter of fact, sometimes you go to amusement parks and things like that, or you actually, in very practical ways in robotics and other things, you see those kind of things going on. You might have had something hooked onto this, and then maybe there was then something attached here that then hooks onto something else. So this is how you can start to build up these devices. And then once you understand what's going on with this piece, you can then understand the behavior of some other point on that, and then once you're onto that, you can move on to some other connected segment. So that's how you oftentimes will do the analysis on these things. Okay. Let's go back now to the cycloid, and maybe I'm going to put one of these up here on the board or on the overhead, and we'll look at it, and maybe you folks could pass those out to everybody. And let me have the remainders. And then I have a second one here as well. Okay, here I want to show you this. Here's what we did last class session. Okay, so here's an image of the rolling wheel, rolling ball, with the associated equations. And my drawings are slightly different in the approach I took on this handout. So what you can notice here is the description for x. And here's the point P that we're trying to monitor right here where my pen is pointing. So from this defined origin here at the ground, where the wheel is touching the ground, if the wheel has rolled forward, then it's lifted this point up. It's lifted this point up, and that point now is up here. And here's the arc length of the wheel that was raised up off the ground, and that arc length is laid down here on the ground. The tread that was just lifted up here is laid down on the ground, was laid down on the ground there. And there's the rotation angle theta. And so, as I said yesterday, or last class session, the x distance here to get to point P from here is S, get you over here, and then you're going to back up the sine of r times the sine of theta there. So that's where we get this expression, S minus r sine theta, but S is r theta, and then we clean that up and factor it, and here it is. We then crank the derivatives on it, and we get the acceleration and velocities. Similarly on y, the height y here is you go up to r, and then you're going to back down r cosine theta right here to get to the y reading and differentiate. Now what I did on this handout is I took those values at important points in the cycloid's motion, and I'll get this so that it just fits on the screen here. Okay, so all the detail is there, and let me see if that helps with the focus any. Okay, so what you can do is you can study this drawing with these key values here at these different locations to help you understand the motion of this cycloidal path. And you can look right here when the wheel is just, the bottom of the wheel is touching the ground, it's got, the only acceleration it's carrying is r omega squared, straight upward. Straight upward. When the wheel finishes its complete rotation, that point has come back down to the ground, and it comes in vertical, and its acceleration right there is upward again. And what you also want to notice is in this portion of the path that here's the acceleration when the point on the cycloid is exactly at the same level as the center of the wheel. Here's the acceleration terms back to the left here. And what I did in this example is down at the very bottom it says alpha equals 0. So I gave the wheel a constant angular velocity just to make life a little simpler. And so when the point on the edge of the wheel is at the height of the center of the wheel, the acceleration is r omega squared to the left. And you can see that the component of it that's tangent to the path here is behind the velocity. Here are the velocity components. And so you can see that it's decelerating. Conversely, as that point is rising on the cycloid, here's the acceleration at the center when it's at the height of the center of the wheel, and you can see that the component of the acceleration is along the direction of the velocity, so it's accelerating right there. Acceleration, deceleration. Okay, so it slows down as it's coming across the top. Remember last session we talked about the speed at the very top of its rotation is twice the speed of the wheel moving forward, and it slows down till it comes in with a 0 velocity down here, and then it lifts off again, comes back up. Okay. The second handout I gave you is similar. More of the same. And I carefully drew it. And calculated the velocity. here's the speed that it has at any location. So I just took the kinematics, like you had in the last quiz, the rectangular kinematics, and worked up the speed in terms of the omega and theta for any location theta. And here is distance r, little r, from the pole. From the pole, being the origin of coordinates over here. So no matter where you are on this path, here's your distance from the origin. And then down below here is the acceleration expressed in terms of generalized alpha, the geometric theta, and omega. Any questions? It's pretty straightforward. And then finally, in a tabular form, down here are all those values at different locations as far as the amount of rotation that's occurred. Okay, so that's a pretty exhaustive coverage of the cycloid. Now, let's see. Someone, Dylan, you had a question from?
Got it figured out.
Okay, good. So we won't respond to it then if you got it figured out. And Alfred, I passed out a solution key to the quiz.